bit of an announcement. Homework got posted this morning, but we have an exam next week. Currently it's scheduled for Wednesday, and that's probably when we'll have it. I might slip it to Friday, but I don't think so. I think it'll be Wednesday. So the homework is due no earlier than Monday. That's what it says on it. I might even change it to make it due Wednesday. I think it might be better for you if it's due Monday, so that you're, a day or two ahead of the exam, right? And it's a kind of long homework. Anyway, so do a week from today, unless you further notice. Any questions about anything? Yeah. For the homework that's coming up? I'll post them, yeah. Sorry, I've gotten a little behind in my posting of homework solutions. I need to catch up, I know that. Oh, and I keep forgetting, I need to bring in the exam, average. I apologize for that. Okay, so. We pretty much beat the particle in a box to death. And I want to mention now a more realistic case. And I only talk about it a little. I'm going to talk about it mostly because it's physically quite important, although mathematically we're sort of going to punt and not really go into it in this class. And that's a simple harmonic oscillator. Okay, and I think you know what that is. That's what happens when you have a force of minus kx, basically a spring, right? Mass on a spring. For which the potential, and in quantum mechanics we want to talk about potentials rather than forces, is that. Now why do I bring this up? Well, the particle in the box was interesting, but not very reasonable. It assumed not very reasonable physically, right? It assumed an infinite potential. Then it was fairly tractable. We solved it easily, but that's not a realistic physical situation. This is a very, very common physical situation. In fact, I don't know if you've heard this before, and of course this is more just a comment from classical mechanics, but do you realize that the simple harmonic oscillator it arises under a very general condition? Do you know what that is? When do you have a simple harmonic oscillator? Perfect spraying, well, what? Huh? When there's a restoring force. But what is that condition that there's a restoring force? It's essentially whenever you have a situation where something is stuck by forces. Whenever, okay? Why is that? Let me try to sketch the potential for something that's stuck. Okay, this is energy. This is the potential U of x for something that's stuck at some location x0 where there's a minimum there. Let me try to draw it in toward the minimum, right there at x0, right? And if I just say in general, now I'm stuck right here right now, but I really don't have a force that's sticking me. I mean, ignoring friction, I could be slid sideways, so that doesn't count. But for instance, all the material in the room, all the atoms in the room and all the solids are at some location, and you can think of them, well, if they're at some location, every atom in your body, it's because it's stuck there by a potential like that. And we can say in just general terms, U at x, let's do a Taylor expansion about this point x0. Okay, I just do a Taylor expansion, right? U at x0 is whatever value this is. Let's just call that u0, okay? This term, du dx, well, by definition, I'm evaluating this at the minimum, and the minimum is where the slope is flat. So this is guaranteed to be 0, right? The slope of it is 0 where it's at its minimum. That's also like the definition of a min-max problem, if you will. And this term here is just what we call k, right? So if I reintroduced a slightly different variable, x prime, which was just the difference between x and x0, right? And also, if I also just say, look, any energy scale, I'm kind of free to like change it by an overall constant, except when we were in special relativity and we pointed out that there was an actual absolute of energy in the relativistic sense. But just when this style of problem, right, I can add a constant to my potential. So basically, I'll just take this to be 0. Then I can say u of x prime is 1/2 kx squared. Right? That's it. Where k is whatever this is. It's the second derivative of the potential. So all I'm saying is that it is just a feature of any curve that has a minimum that at the bottom, right there at the bottom, if I do a Taylor series and I throw out these terms, which is always valid if I look at a value of x close enough to x0, all I'm left with is the quadratic term, okay? Which is to say there's a restoring force. Anyway, that's just to point out that this is of great general applicability, right? And so it's worth looking at. Now, the Schrodinger's equation for it, again, I'm just going to look at the time-independent piece. Is that, right? And I should solve it. As you can maybe guess, this does kind of look like trouble compared to what we've done so far, right? Because I've got to take derivatives of psi, and then that's got to be proportional to psi somehow, but I also have to end up with like x squared there. So it's not so simple. I mean, a simple sine or a cosine isn't going to hack it. How am I going to get an x squared there? All right. And at this level, of course, we punt. We're not going to solve this for you, okay? But I think it's important enough, just the results, that I need to quote them and make you familiar with just a couple of points. The first is that you do indeed, so let me sketch the potential. And I'm drawing it steeply. All right. The first point is that, like the particle in the box, you do get discrete solutions, right? There's an integer that's associated with the solutions. The lowest solution, and again, I'm kind of combining, it's got some lowest energy, E, we call it E0 in this case. And now I draw the wave function there. I'm also putting psi on the same drawing, right? It looks pretty much like the particle in box solution, okay? But it's not a sine per se, a sinusoid per se. Then there's another one, and not surprisingly, that has, goes down and up and kind of comes back to 0 there, etc. Dot, 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 dot. So these look kind of like the particle in the box solutions. The energies are a little different. The formula is this. N plus a half times h bar omega, where omega is the standard harmonic oscillator frequency, okay? And n, in this case it runs from 0, 1, 2, 3, a little different than the particle in the box. Importantly though, when n equals 0, there's still energy, just like the particle in a box. So that kind of interesting feature of a quantum mechanical system survives. There's the lowest possible state of atoms. Think about what this means. This is actually interesting, right? This speaks to like what you might think about in terms of absolute 0 temperature. If you absolutely cool a material, a solid, and I argued that every atom in your body, or in any solid you can imagine, or any liquid you can imagine. It's got interactions with its neighboring particles. And you know, if it's stable, this has to be a description of what's going on. Therefore, this is the right, you know, mechanics of it. And the answer is that this is the energies, and so the lowest energy still has an energy. It's called the 0-point energy, 1/2 h bar omega. Okay, so even at what you would call absolute zero of temperature, if you could attain it, every atom has some energy. It's not completely at rest. Just to give you a sense of what these solutions are like, and there is sort of a class of problem where I could give you the solution, and I could say, you know, show that this gives you the right, you know, show that this matches. Well, sorry, it's a constant times e to the minus 1/2. Sorry, I'll give you a wave function, and I'll say show that that is a solution. That's what we'll do real quick. So it's something like, it's this. It's a constant times e to the minus 1/2 b squared x squared, where b is a constant and happens to have this form, mk over h bar squared to the 1/4 power. Okay? And if you're interested, c, when you properly normalize it, is the square root of b over the square root of pi. Anyway, so that's the solution. Higher solutions, this is the 0 one. This is the one I've sketched here. See, it kind of looks like the sign, but it's actually more like a Gaussian. Okay? Higher solutions have powers of x out front. In fact, as you go up and higher, you get a whole polynomial in x. Like it'll have an x term and an x cube. This is x to the 0, then the next one has an x squared, and the next one has like an x fourth, etc. Okay? And these are listed in the book. Just to show how this works out, what's d psi dx? I'm going to plug this into the Schrodinger's equation. So let me just first take the derivative. I take the derivative of this bit, which is going to be minus b squared x, right? You can see that, right? That's all that'll come down out of the exponential. Okay? And so if I take two derivatives, okay, first I take the derivative of this and then that. So the derivative of this is minus b squared. It's going to multiply by psi. I'm going to put that outside. And now I take the derivative of psi again. Remember, when I take the derivative of psi, I just get minus b squared x psi. So this is plus b fourth x squared times psi. Okay? So that being the case, if I plug the second derivative into this equation, I have minus h bar squared over 2m times this, which is b fourth x squared minus b squared. Now what was b fourth? B was the quarter root of all that. Well, let me just not skip steps. It's plus b fourth x squared minus b squared times psi plus 1/2 kx squared psi equals e psi. So now psi cancels out. And now let me plug in minus h bar squared over 2m. B fourth is mk squared. No, mk over h bar squared. X squared minus mk over h bar squared. Okay, to the 1/4 power squared is to the 1/2 power. Plus 1/2 kx squared from there equals e. And if you stare at this is 1/2 kx squared. And that's minus 1/2 kx squared. Okay? And Oops, and I forgot this term here. Okay, and this beast, that's h bar squared to the 1/2. It's h bar in the denominator. It's m to the 1/2 in the numerator and m in the denominator. So this is 1/2 h bar square root of k over m equals e, which is 1/2 h bar omega, based on omega equals square root of k over m. Okay, I wanted to show you that this fits. In fact, how in the world did people dream something like this up? Again, to solve a differential equation, really all you got to do is guess. Once you've kind of realized the key is to have the x squared there, and then when you take two derivatives, that pulls down a term that's in x squared. And so then in general, what you do is you write, well, maybe there's an x out front, and people will write down, well, it could be any n, x to the n. And so then you plug in and you work out these relationships. And so there's kind of a brute force way to do it, and it's tedious, and I'm not going to go forward, but you see that it does fit. And this is actually, sort of homework / exam problem would be, here's a Schrodinger's equation, is this a solution? Or show that this is a solution. Right? You plug in and turn the crank. Maybe I'd ask you to find a constant, say. Okay? So that's the type of solution, etc. I have one last comment here, which is that as n gets really big, if this is the potential, I sketched the lowest order solution here, which was this is psi 0. Okay, we go up for psi. Now, if you get to very large psi, turns out it looks kind of like this. This is for n large. In other words, the probability, the wave function is big over at the edges. And the p of x largest at the edges. Right? That actually is classical. Have you ever thought about this for a simple harmonic oscillator? Let me be a simple harmonic oscillator. If I go over here, and then I come back like that, and then I slow down. I'm probably not doing pure harmonic motion, right? But it's just a very simple thing. If something goes back and forth in a kind of obvious way, where do you spend most of your time? At the edges. When is the length of the day the least changing, and when is it changing the most rapidly? Summer and winter. And right now is when it's changing the most rapidly. It's the same idea. It's a property of a sinusoid. Okay? You race through the origin, you slow down to turn around, and you spend your time at the extremes. And so this pops out of mathematics I'm not going to show you, but you can look up. They have the form of the wave. I think they have the form of this in the book, or they show the first number, and you see it starting to do this. And that is something, and I mentioned it last time in class, there's something called the Correspondence Principle. As n goes to infinity, you get your classical solution. It's not always completely clear exactly what it means, or it'll be like the classical solution. I mean, I still have this kind of probabilistic behavior. I'm still just going to compute a wave function, and I'm still going to have a probability that it's over at the edge that's bigger than in the center. So it's not exactly the same as the classical solution. But nonetheless, there starts to be an analogy, whereas this doesn't have any element to the classical solution to it. The notion that if I have a mass on a spring, it always has some energy. That's just that's just purely quantum mechanical. I mentioned it last time for the particle in the box, and then I don't know if you noticed, but I kind of looked puzzled because I just said something wrong and when I did it. However, I put it in your homework to work out the right version of what I meant to say. And that's to look at in what sense is the particle in a box, the expectation value for x and x squared and the dispersion, you're going to compare that to the classical result, okay? It's actually pretty straightforward, but I put that in the homework, okay? But so all of these problems where there's an n, if you take n to infinity, you ought to kind of sort of recover the classical result. It's called the correspondence principle, okay? Oh, and just one other final comment. Another physical system that this is a good sort of model for is actually even just an atom alone, the electron in a shell, in an outer shell of an atom. We're going to sort of solve the hydrogen atom later, and it can get quite complicated. But if you just ask a simple question, like if something just barely tweaks an electron in an outer shell of an atom, how does it behave? And the answer is, it more or less, it acts like a simple harmonic oscillator. So there's a very simple classical model, for instance, of light scattering off of an atom. It explains Rayleigh scattering, why the sky is blue. Okay, and you just treat the electrons in an atom like a simple harmonic oscillator. Okay, or even if you have atoms colliding with each other. If they're colliding gently and there's not like a deep, strong interaction between them, you can basically solve, and it's more complicated than we're talking about in this class, but again, just treating the electron stuck to the atom where there's sort of a defined orbit, as you kind of say the orbit's stable and deviations from the orbit are like a harmonic oscillator. So this is just really, really widely applicable. And that's why I wanted to show it to you. And it is interesting, too, that the energies just go, well, I erased it, but the energies just go linearly, not like n squared. Or not like in atoms, where, as we'll see, it goes like 1 over n squared. It just goes n, right? All right. So now, these were, okay, so we did particle in a box, and we did mass in a spring. Both of those problems, the particle was stuck, bound. Bound is the language. But what if we don't have a bound particle? We started off talking about free particles, and we solved that, and just simple plane wave. But what about situations that are sort of in between? So I have a potential. I have a potential of some sort, like that. But the energy can either be high enough that the particle it'll see the potential but not necessarily get stuck, or maybe it's stuck. And how do we talk about that? Let me give you one quick analogy. And again, this is a classical mechanics problem. You may or may not have seen it this way. But it illustrates exactly the difference between bound and unbound states. And I'm thinking of orbital motion. Okay, basically something orbiting a planet, right? So with gravity. I don't want to do a big sophisticated analysis. Let me just write the energy particle m and some particle little m coming in, separated by some distance r. Okay? What is the energy? It's the kinetic energy plus u, the potential energy. Okay? Remember that for the kinetic energy is 1/2 mv squared. And if I want to think about something that's moving in r and theta, so let's just a two-dimensional problem here, I can say if r is the vector out to where the particle is, that's r, the magnitude times r hat, and dr dt, I hope you remember this, is I can take the derivative of that times r hat, but then I should also take the derivative of r hat And I get that it's r theta dot d theta dt. Okay? You remember that? And so velocity, and this is the velocity. So the velocity squared is dr dt. In fact, sorry, I'm getting tired of writing dr dt. R dot. Just putting the board down here. You guys familiar with this terminology? Calling R dot dr dt? Yeah.
In the with the line, shouldn't the like R theta dot d theta dt be like R theta hat?
I am sorry. This is d theta dt. I'm pretending I hadn't told you about theta dot. Is that. And if you say something is dot, that's a shortcut for saying d by dt. So R dot is that. This is d theta dot. This is theta dot. Okay? So then the velocity squared is the square of this vector, and theta hat and r hat are orthogonal. So it's r dot squared plus r squared theta dot squared. You're not going to be responsible for this because this is, I'm just showing you this as an analogy, but I think it's nice. Okay, so that's v squared. Finally then, the energy is 1/2 mv squared. And the potential for gravity is minus g big M little m over r. Okay? So that's the energy of this little mass coming into this big mass. Whether it's going to come right at it or whether it's going to be in an orbit, we don't know yet. Okay? There's one other concept, which is that there's angular momentum. mv cross r is the angular momentum. And it's conserved. It's conserved in this case because there are no torques, right? If I have just gravity, it can't make a torque. Okay, and mv cross r, I can either remember that this is just m r squared theta dot, or I can get that from taking v and crossing it into r. Okay, r hat cross r hat is 0, but then this crossed onto that gives r squared theta dot with an m. All right? And if that's the case, then theta dot squared, just solving this line, because that was a vector, this is just the magnitude, so theta dot squared is L squared over mr squared. Okay, so let me plug that in here, and I have that the energy is 1/2 m r dot squared plus this is L squared over 2m r squared. If you think about plugging this in and squaring it, I'll have m squared in the denominator and an m in the numerator, and one power cancels. Similarly with the r's. All right. Huh? This is v squared. 1/2 m r dot squared. Oh, how did I get this equation? I'm sorry. I meant to square that, and I meant to. I'm sorry. That's theta dot squared. I think I was not trying to square it here. Yeah, I shouldn't have written squared. All right. All right, so that's my energy. And that'll be a constant. Have you seen this written this way? Anyone not? Yeah. Okay, why did I do this? Okay? This thing here is sometimes called an effective potential. The point being, the energy has theta dot squared. Energy is complicated. It has how much am I orbiting sort of sideways and how much of my orbit is directed radially. But I get to eliminate one of the two unknowns, if you will, because the angular momentum is constant. And I get to write an expression just in terms of r's, or r dot. And then what's nice is I have just this piece, which has no velocities in it. It has neither a theta dot nor an r dot. I mean, it does in the sense that L has that, but this combination of things was constant. So that combination of a theta dot and an r was constant. So I get to eliminate it. This acts like a potential. And so all of this has been away. Actually, this drawing was reasonably accurate, but let me just start from scratch. So versus radius, the gravitational potential looks like this, minus g m over r. The other piece, L squared over 2m r squared, I'm sort of ignoring the values of these constants, and I'm just drawing 1 over r there with a negative sign. This, of course, is energy, be it kinetic or potential or whatever, and that's r. This is 1 over r. 1 over r squared is smaller when you get big, and then stronger when you get small. So that's L squared over mr squared, with a 2 out front. And when you sum the two, this one wins out here, because 1 over r for big R is bigger than 1 over r squared. But for small r, 1 over r squared is bigger than 1 over r. So the sum of them does like that. So this is the U effective. Those two pieces. And so a way to think about the system, it's a very simple way, is if I have a kinetic energy, I'm going to change my sketch just a little bit to give myself more room to draw. I'm not going to change it qualitatively at all. I just want to move my lines a tad. Okay? That's U effective. Okay? If I have a kinetic energy down here, or if I have a total energy down here, okay, then what happens on this orbit is the sum of this piece let me rearrange that. 1/2 m r dot squared equals E minus U effective. So think of that, 1/2 m r dot squared. That's like, I don't want to call it kinetic energy in radius, because, well, in some sense that's what it is, but it's not good. You don't think of the kinetic energy dividing into different components. But it is a kinetic energy term just due to the radial part of the motion, okay? And what it's equal to is how much energy I've got minus how much energy is tied up in potential, all right? So if you're a particle with this amount of energy, without solving anything else, I can tell you exactly what it does. It comes into this point where these two lines cross, and the difference between E and U effective is 0, and there it turns around. And then it goes back out and it gets to that point, and then the change in the radius with time goes to 0, and it comes back in. So this line here, without knowing anything else, I know that that's some sort of elliptical orbit where that's the value of R1, and that's the value of R2. That R and that R are this distance and that distance, and it's just whizzing around. Okay? Sitting here right there, where dr dt is 0, because the energy, if I have an energy which is exactly that point, then there's no, then this term is 0. That's a circle. All right? Okay. What's germane to the current, what I wanted to show you about quantum mechanics is those are bound systems. I could easily have the energy out here. It's just a higher energy. What does that mean? That means if I go off to infinity, the potential is 0, and I've got kinetic energy equals 1/2 mv squared equals that energy, whatever it is. And there's no potential. And then as I come in, I come to this point, and the potential, I'm sorry, this one part alone. This is the total potential. I'll come to that point, and then my radial change goes to 0, and I'll turn around and go back out. Okay? That's an orbit that's like that. Could be a parabola or hyperbola, right? And it's not bound, and it just goes on out to infinity. Okay? So that's a lot of analysis for the problem, but you got to keep that sort of notion in mind, right? So that's the difference in physics between bound and unbound behavior. Bound and unbound orbits. So we'll often use that language, orbit. Okay? All right. And you see the key thing was whether or not if I choose a potential that goes off to infinity, if I choose a potential that goes out here into 0, the question was the energy greater than or less than 0? Or analogously, if the potential didn't go to 0 out here, but just to some value, the question was off at infinity, was the energy larger than 0 or not? Larger than the potential or not? If the energy was larger than the potential, that means off at infinity, I still have kinetic energy. That means I just get to race away. Okay? There, of course, is an orbit where I have 0 energy off at infinity, and I'm sort of moving infinitely slowly, and I pick up a little bit of speed as I come and I come and I come, and I come in and I zoom down and I come back out, right? And then I go stop at infinity. You know, an infinite time, I'll stop with 0 energy off at infinity. Okay. And that's the just barely bound orbit. All right. So I think it's worthwhile keeping this sort of idea, this general idea of bound and unbound orbits and how they relate to energy. That's actually a very useful thing to know just in general. And you see, although I did have to do a little bit of algebra here, I actually you can learn a lot about orbits without having solved in gory detail. I didn't take F equals ma and integrate it and find solutions. And yet I learned a lot about the orbits. Okay. Well, so let's start with, I guess, probably the simplest, one of the simplest examples of a situation like this in quantum mechanics. And that's just to do a finite well. All right? So let's do it like this. Again, this is energy. That's space. I'll go from 0 to L with my well. But I'm going to put U equals 0 here. U equals some constant U0. In regions 1 and 3. And region 2 will be just like for the infinite well. So this is just the case of the particle in a box, the classic particle in a box, but instead of taking the potential to be infinity, which is not physical, I'll take the potential to be finite. Okay? And now all of what I just dragged you through a moment ago applies in the following sense. I can expect that if the energy is up here, this is unbound. In other words, I can have a reasonable kinetic energy way away from the potential, and that will just be a particle racing around as a plane wave. Then something will happen when it gets here, okay? But it can clearly just move away. And that will be unbound. But if the energy is less than U0, okay, classically, in fact, I can't have anything here. right? If there's some potential energy, classically, if my energy is less than the potential energy, I can't go there. I mean, it's pretty straightforward. There's some MGH required to get to the top of this table. And at my age, with my knees, I cannot jump on top of this table. Okay, at least not from a standing still. It isn't going to happen. Classically, it's just not allowed. I don't have enough energy in me to lift up and get there. Quantum mechanics, as we're going to see, is a little more subtle. But certainly I have some energy, the particle has some energy here, and this will be bound. It's not going to get out, but it's going to be a little bit different than classically in terms of it like really can't get out. All right. So how are we going to solve this? Let's stick with the bound case. So we'll start. We'll start with the potential energy being greater than the total energy. That way. So we have the Schrodinger's equation in the three regions. Let's look at case 2 first. It's quite simply that, right? Because the potential is 0. And I already know that psi is going to be sine or cosine. And I'm not going to reprove that by plugging these back in, because we already did that. We know that k is the square root of 2me over h bar squared. Right? Because we already did that. What I will anticipate, and as you saw in your homework, for instance, where we put the particle in the box and shifted the origin, it takes some practice to know what to do. In general, if you're not sure, you basically should either try both sine and cosine. Sorry, and if it's the exponentials, you have either a choice of plus or minus ikx. You should either try the combination of those two or the combination of the plus and the minus of these two. So I'll choose this. Okay? And that's going to be in region 2. And I'm not right up front going to throw out either. Okay? What about in 1 and 3? So this is Schrodinger's equation. Okay. Now I have plus u times psi equals e times psi. And let me just go ahead, because u is a constant, and rearrange it right now like that. Okay? Nothing other than I just plugged in u. Now, this is not a healthy thing, because I know that this is less than 0. I better rewrite it and have only positive constants so I don't get confused. Okay? So that's all I do, is I rewrite it. All right? So now I have a minus sign on either side. Actually, let me, I'm going to go ahead and multiply by my constant. Okay? 2 derivatives of psi is equal to a constant times psi. Okay? That should come as no surprise that psi better be e to the alpha x or e to the minus alpha x, right? I no longer am going to choose sines or cosines or e to the ikx because I'm taking two derivatives and I don't need to introduce a minus sign, which I get from the sinusoid choice, or putting the I there, which gets squared and gives me a minus sign. Okay? Now let's just try either one of these. If I take this one, take two derivatives, plug it in, I think it's pretty clear that alpha squared is 2m over h bar squared u0 minus e, right? That's pretty straightforward. You guys see that? Right, just from plugging in. You need to be able to do this sort of algebra, and not just in this class, right? This is like the first time of many, many times you're going to have, algebra like this. I go fast, but I've seen in exams, there's a few people that probably thought they understood, but they never really wrote this down, and they get to an exam, and you basically have to do that and freeze up. Okay, you got to be able to do this, all right? Okay, so that's the case. So now I get to choose, though. I get to choose, do I have alpha x or minus alpha x? In region 1, I'm going from minus infinity to 0. Right, that's what x does. Right? It goes from minus infinity to 0. If I choose e to the minus alpha x, then at minus infinity, what do I get? I get e to the alpha times infinity, which is infinity. So that's not allowed. All right? And this type of reasoning is just really common. I have to choose psi 1. I used constants a and b, so let's call this constant c. That's my only choice. Okay? Similarly, in region 3, having made that sort of argument, you can see that I have to choose the negative sign. Okay? That, when I plug in positive infinity, will go to 0. If I'd had alpha x, it would go to infinity as x goes to infinity. Right? Everyone get that? So there I am. I've got my my starting point. So it's just like we had before, but my starting point isn't like one sinusoid, sine kx, which I had for the particle in a box. Or I might have tried cosine, but it wouldn't have worked. I've got 4 terms. So I've got 4 unknown constants I've got to solve for. Okay? Now actually at the end, one of them is going to come from what? Can you think? There's always something that gives you... So, sorry. Yeah, I've got 4 constants. K is determined, alpha is determined, so it's just A, B, C, D. So there is one constant that's going to come from one thing, which you should know. I'm always going to have to normalize the wave function. So at the end of the day, one constant is going to be determined by normalization. So then I've got 3 constants left, and I'm going to need sort of 3 equations to determine them. Okay? And so now that we're out of time today, we'll do it Monday, but that we're going to get from looking at the boundary conditions. We've got to match up the wave function at x equals 0 and x equals L. All right?